Common use is you should read that shared section because I put a message in there for you. But you can use them for just about anything, and they've got all kinds of nice APIs, like you can wait for multiple events and do things asynchronously with them. Semaphores are a thread synchronization mechanism, and all these objects can be named. I'm only interested really in named ones. One of the things that's interesting about naming a thread synchronization mechanism is that almost every thread synchronization protocol that you'll come across is cooperative. So, there's no such thing as a trusted a thread synchronization scheme where you don't trust the other parties to try and not be creating bad deadlocks or whatever. So whenever you see a semaphore or some kind of thread synchronization scheme exposed with a name, you have to worry a little bit. Even if they're local only, you better lock down those ACLs pretty tight, because if any other user can access them, there could be issues. So you can use them securely for things, but it's a big red flag. And what I look for from a design perspective when I see a semaphore being used in a named way is, who are the other people I'm sharing this with? Do I really trust those processes? Is there any identity or privilege gradient? We want to make sure that when we look at our process, we see all the different attack surfaces, and if this is in the exposed surface, then there's usually something going on here. Either this thing isn't being used for thread synchronization, it's being used for some other side effect, or there's probably an issue, or at least a substantial risk that you're accepting. So these techniques that I'm talking about have a couple of goals. One of the goals is to identify vulnerabilities, local or remote, in applications. We've got, as I've said a couple of times, some binary that we're looking at. Maybe it's some kind of service, and we want to make sure that every part of the attack surface of this application has been covered. And we knew, oh yeah, this thing listens for connections on port 25. We're used to that, and we know that it accepts files from users, and we've got a antivirus scanner, and we've checked the parsing routines in there. But when you're looking at it, you have to also see, hey, are there any additional surfaces, attack surfaces, places where input come in that I'm not aware of? And you might be surprised how many of those you find. I know that when I ran the pipe list utility for the first time, I was kind of surprised to see 80 or 90 pipes jumping out on my laptop, which is just running PGP disk and maybe some VMware and stuff, and there's this huge number of pipes. Anyway, so we want to identify local or remote vulnerabilities for privilege escalation. Localhost privilege escalation is the main one, but remote would be good too. So our secondary goal is that we want to work on applications in binary form. So we've got all these libraries, COM objects, dependencies, operating systems that we don't have the source code for. Or if we do have the source code for them, they're so big we don't have time or energy to go through them all. Even if there are bugs in them, they're not our bugs. We don't necessarily want to go through the hassle of understanding them all. It's a very common security auditor's dilemma. We just want to be able to trust the things that we can't review. And so working on binaries is going to be a really important part of that. Also, these test tools that we develop, we're going to spend a little time putting together some tools for testing, and they should be as integratable into the regression tests and reusable in the testing process as possible. And they should be as static as possible. Once I'm done building this thing, I'd like it if I didn't have to change it just because I added one more interface or I've changed the protocol a little bit. If you make a nice fuzzer that knows the protocol and speaks it really well, if you change that protocol at all, you have to change your fuzzer so that it can test the new parts of the protocol. One of the things that we'll be doing is making ours a little bit more independent of what actually is being communicated. And that's going to allow us to minimize the change to our tools for new versions of the software. It's going to let us reuse this fuzzer on all kinds of different products. So, unfortunately, fuzzing isn't a silver bullet. Ideally, we'd of course want to find any kind of bug, but in practice, we're limited to certain types of bugs. So obviously, the ideal bug would be something that crashes the application. Application crashes don't go unnoticed you can get your postmortem debugger to pop up. If you have some exceptions, that's great. Good logging would be the next best thing. Anything that puts the system into an inconsistent state, screws it up, makes the CPU spike, uses up all the memory, that's going to be good enough that probably if you have a real tester sitting there looking at the machine, or an automated set of tests that expects the tests to finish within some reasonable amount of time, or with some reasonable maximum CPU load, you'll be able to detect it automatically. So what kind of bugs are good for this? Well, we definitely want to target applications written in C and C++. These tend to have a lot of technical bugs that aren't application domain bugs. By application domain bugs, I mean, if you have an application that does some type of complicated function that, maybe it grants access to a checking account, right? Figuring out what's going on inside that domain isn't very reusable, because the next application you look at isn't using checking accounts, it's a video game or something. So, fortunately, there's this huge class of bugs that afflict all software, and they're things like integer overflows, heap and stack overflows, pointer problems, any type of memory corruption issue. And these are also great because the operating system works proactively to detect the conditions. If you write to some offset in memory that's chosen at random, the odds are you're going to get a protection fault and invoke the debugger. So makes it easy to detect, makes it easier to debug, because the errors occur in a way that sort of points to what's the cause of the problem. And some of them are a little trickier, like with parser bugs or double free bugs. You can get a lot of conditions where the code crashes a long time after the actual corruption occurred. And certainly with fuzzing you find a lot of those, but they tend to pop up later in the development life cycle, or later in the testing cycle. So maybe with your first pass you find a bunch of the more obvious bugs. And then as you go on and the thing starts making it running longer with the fuzzer on it, then you start running into these kind of harder corner cases, and that's not as big a problem. So the bugs that this is no good for are these domain-specific bugs that I was telling you about. So I've used SQL injection as an example here, but SQL injection, actually, if you've got the right kind of application level auditing, like say you have application level auditing that reports SQL errors whenever a SQL statement is submitted that doesn't parse, right? Oh, the syntax is wrong in this statement. That's exactly the kind of debug code you should have in your application. It's exactly the kind of warning you need to know about. And in the QA phase, this is going to make the fuzzer could actually find some SQL injection issues. Command injection is a lot harder. If it does run a command, the odds are very low that it's going to be something that makes sense. The best you could hope for is some kind of systrace thing. It's not really happening. Authorization bypass. As you can imagine, if you've got some kind of authorization scheme, like check to see if this is the right account before you take the money out of it, right? And some fuzzing allows you to bypass that, it's not going to find it. Authorization bypass, a whole bunch of these bugs, basically things that are in the domain of the application itself, aren't going to be detectable. Also, backdoors, any kind of intentional bug. So when a developer decides that they are going to put in a little present for themselves if they ever have to retire, those types of bugs can be found basically through source review only. You're not going to find them accidentally through fuzzing. And then, the security and design bug where, we decided to implement this really bad idea. Like, what my application does is it waits to see if it's Friday, and if it's Friday, it decides to go look on the internet and see if, this website has a posted zip file with a number greater than the number of the last one I downloaded, installed, and ran. And if it does, I'll run it. That kind of poorly designed, insecure automatic update scheme may respond very well, fuzzing isn't going to show any problems with that. It's the design that's screwed up there, not the implementation. You can have a great implementation of that terrible design. So, naming and creation attacks. So these naming and creation timing attacks are unfortunately closer to the domain of the IPC mechanisms themselves and still can't really be found. These are design issues again. So name squatting attacks are when, if you have a client that connects up to a server And the way it finds it is it connects to a name pipe named foo. And it says, oh, foo, tell me what to do. And the server says, oh, get these updates. You need new antivirus signatures. You need whatever. And it just trusts it. Well, a name squatting attack is going to be very effective if the attacker can run code before the server reserves the name. It can also be a real problem on a network, because if it's going across the network, as I mentioned before, those clear text protocols might not give you integrity protection or confidentiality protection. An attacker might decide to set up their own server with the name of the server that you think you're going to and put a pipe on that. So that's that name squatting attacks. These fuzzers won't help you find those kinds of bugs. Race is prior to DACL establishment. So when you create an IPC object, you've got two options. You can either set the ACL right then, or you can add the ACL later. And yeah, it might seem like kind of a bad idea to add the ACL later, but it's somewhat popular. And it creates race conditions. If you've got this thing that anyone's allowed to connect to just for a few milliseconds, that's when the bad guy will connect. So these would be great bugs to be able to find. And I'm very glad to say that we can't find it, because then I can keep my job. So, but I wouldn't be giving this presentation if they could, I guess. So, viewing of IPC objects. So when we're first looking at IPC objects, you kind of got to get a feel for what these things are. You may be surprised to find out that components you're using, or libraries that you're using, or software that you've installed uses some of these mechanisms, and you never knew it. And you might even be surprised to find that they don't ACL them correctly, or ACL them in a way that you wouldn't consider secure. There's a company called sysinternals that makes some great tools. When I wrote these slides, they weren't. They were a separate company. Now they've been bought by Microsoft. So these tools are available right now on their website, though, and are great. One of them is called Process Explorer. Process Explorer, well, I'll show it in a minute. Another one's called Handle. It's a command line version of Process Explorer that's kind of less powerful, but it's good for parsing its output if you want to use it in programmatic, like maybe you want to write a little Python script that digs around on your system and finds IPC mechanisms to test. None of these tools are affiliated in any way with ISEC. We're just big fans. And you can kind of think of some of these tools like a super version of LSOF for Windows, if you're familiar with that Unix tool. So here's a picture of, oh, I wonder if I can actually point here. Here's a picture of Process Explorer. And you can see I've got the call logger here. I've selected it. And when you select it down on the bottom, you're getting a list of all the handles that it has. And the handle I've highlighted is one that's called device named pipe call logger. And I've asked for the properties, and then I've asked for the security properties, and then I've gone into the ACL. And this lets me see, oh look, everyone's in that ACL. Fortunately, that everyone is read-only everyone. But it lets you just dig in, and you can go by process. Oh, I'm worried about this particular process. Oh, I'm worried about this particular section, and dig through and see which processes are using it. It's pretty good. And then handle. Here's the exact same thing, only with the command line version. So with handle, you can see the same call logger process being accessed. -p call logger tells it to find that call logger program. And you can see the file there.